this morning is by Tyler Helmuth from Bristol, and he's going to talk about algorithmic Pirogov-Sinai theory.
Okay, so thanks a lot for the invitation and chance to speak. So it's sort of a continuation of what's been going on this morning in terms of polymer models and cluster expansions. What I'm going to talk about is joint work with Will Perkins and Husret. So this is sort of the thing that Will pointed to in the morning as being the first paper that sort of started off some of these ideas. So as you can see from this slide, it's a subset of Z2, and there are sort of two sets of people. There are people where you say, choose your favorite graph, and they immediately say ZD and refuse to consider any other graph. And that's someone like me. And then there's most of the other people in the audience here. But this talk is just going to be about ZD. So the motivation is very similar to the animations that Will showed at the beginning of his talk for the POTS model, but in case you didn't see those, I'm going to consider the hardcore model instead. And I just want to know, what does an independent set look like on the hardcore model as I vary the activity parameter? So if lambda is very small, I don't see very many particles, so the picture looks something like this in a little square in Z2. But if lambda is very large, then we start to sort of fill up the volume quite a bit. So we see something that looks roughly like this. Okay, so there's no animation of showing you the difference in behavior between these two extremes of lambda, but we know that sort of for independent sets, which we've talked about a lot during this workshop, that as they get full, we sort of know what things are going to look like. So just to fix some notation for how I'm talking about independent sets, this is the partition function that I'm interested in. So it's going to be a sum over all independent sets on my graph lambda to the size of the independent set. So the probability of any independent set is just proportional to the weight it received in here, normalized by z. And this fact that there's two different pictures is, was first sort of made a rigorous thing by Dilution, who said that if the dimension is at least 2, remember I'm only talking about ZD, so D is the dimension, not the degree anymore, then there exists a phase transition. So I'm not going to use this anymore, so maybe I can shut the distracting animated GIF. So let me just make let me make this a little more precise, what it means that there's a phase transition. So to do that, I'm going to let J be an independent set on all of ZD. And I'm going to define a new partition function that has J as its boundary condition. So what that means is that now I'm going to sum over all independent sets, again in ZD, that are the same as J outside of lambda. And then I just take lambda to the size of the independent set, intersect the set lambda. So it's just counting the number of particles.
Sorry, what was lambda?
Lambda is some finite connected subgraph of ZD. Yeah. So like my box. So as long as it's a finite region, this is a well-defined object. So if I do this, what I get is I get a collection of probability measures that are going to be indexed by the set in ZD and also by the possible boundary conditions. So I get a set. Like this. And the precise thing that Dilution proved is that So if lambda is very small, there exists a unique weak limit of this set of probability measures. And if lambda is very large, there exist at least two limits. In particular, the measures I get if I consider the even boundary condition and the odd boundary condition are different. So I'm using E and O to denote the independent set that just occupies all the even vertices or just occupies all the odd vertices. So we have a very precise idea of what an independent set looks like in the sense of knowing that there's a phase transition, but we could ask a much stronger question that people here would naturally ask. How do you sample one of these objects? So sampling, or what does one look like, not just in an asymptotic probabilistic sense about weak limits, but what does one look like in terms of seeing a picture of one? So what's known, the most natural thing that you could do is use Glauber dynamics to try and simulate this, like Will was showing for the Potts model. And if lambda is very, very small, then Glauber works. So that was known a long time ago. Someone here probably knows who did it first. I'm not totally sure, to be honest. And there's been a lot of work about improving lambda very small to trying to get more optimal values of lambda, but I don't have time to go into that story. As you can imagine, if the density is very high, then the Glauber dynamics fail. So I think the first example of a phenomena somewhat like this was probably from Lawrence Thomas, and then later on many people contributed to this story, including like Prasad and other people in this room as well. So our goal, and I mean both in the sense of for this talk and also our goal when we started doing this work, was to say, how do we turn our probabilistic understanding into algorithms to approximate the partition function and sample here? So maybe I could say the goal is to turn probability into algorithms. And fortunately, for the sake of this talk, we succeeded. And the theorem we proved is the following thing. So there exists some density that depends on the dimension, so that if you're above that density, then there exists an FP test for the partition function Z lambda and Z O lambda for lambda contained in ZD finite and connected. We did a little more than that. You can also sample. And another thing that you might want to do so also, you can do the torus. Provided that n is even. And the error you want to make is at least e to the minus c, where c is some constant that depends on the dimension. Okay, so in all these contexts, we can approximate the partition function and we can sample. And the way we did it involves this thing called Pirogov-Sinai theory, and I'm going to talk about that right away. It's much more general than for the hardcore model, though. So the same theorem is true if you consider the Potts model. The same theorem is true if you consider the Whittam-Rowlandson model. Most of your favorite discrete statistical mechanics models fall under this framework, and you get sampling and counting algorithms by verifying just a few conditions.
How about free boundaries?
So free boundaries would be okay, I believe, but we didn't check every last delta of the proof. But I'm sure it's okay. Okay.
You'll not be deviating from Glauber, so it will be only Glauber.
I will not use Glauber. Glauber fails, so yeah. So Glauber provably doesn't work, so we must do something else. And in this theorem, it's a deterministic algorithm. It's not a randomized algorithm. Any other questions before I? Yes?
So on the torus, you still have something that is a kind of mixture of even and odd. So which one are you sampling? Sampling both?
Oh, in this case, it's just you could come up with a definition of what being on one side means, or you could just compute the true partition function. So that's the thing you would want to compute. But of course, you do it by reducing to the mostly even and mostly odd. Okay, so what I just said quickly in words, maybe let me write down. Many discrete stack. So it applies to many discrete statistical mechanical models provided symmetric phase. So there's some restriction that you have to satisfy. And what this means is that you have to be at the symmetric part of the phase diagram. And I expect that phrase means almost nothing to everyone here, so I'll explain what that means next as a way of introducing Pirogov-Sinai theory. So the next part of the talk is me telling you what Pirogov-Sinai theory is, and then after that I'll show you how we sort of reduce our problem into that framework. So roughly speaking, Pirogov-Sinai theory is a sophisticated cluster expansion, or a sophisticated polymer model like Will was talking about. And to illustrate the ideas, let's consider the Q equals 3 pots model. For me, I want to write it, the energy of a configuration is that I sum over all vertices in the graph, and I check when the color at the vertex I and the vertex j is the same, and then I add an additional term that sort of favors one color or the other according to some parameter h. So the probability of a configuration is e of h. Okay, so if beta is very large, this is a low temperature scenario, and if beta is small, it's not. And these sort of break the symmetry between the various colors. So the important definition is of a ground state. This is a periodic ground state. So this is a coloring that's periodic, such that for any finite perturbation, so this just means another coloring that only differs from sigma in finitely many coordinates. I only decrease the energy. So particular examples of this, if all of the h's are 0, then just taking all of the colors to be the same everywhere. So all just color 1, just color 2, and so on. Those are periodic ground states. And you call a ground state stable if you know that the limit as lambda increases to zd, the energy of the configuration restricted to lambda is maximal. Okay, so what does this mean in a concrete example? Suppose only h1 is positive and the other h's are 0. So then I'm assigning more weight to the color 1. So then the stable ground state is going to be coloring everything 1, while ground states 2 and 3 will not be stable. Does that make sense before I draw a picture of what it means? So we usually organize that information into a phase diagram. So this is at 0 temperature, so beta equals infinity. Just by normalizing, I can choose h1 to be 1. This is the h2 axis. This is h3. So now I'm just going to label these regions by which ground states are stable. So in here, it's 1. In here, it's 2. In here, it's 3. Along this line, I have 2 stable ground states, so they're said to be 1-2 coexistence. Here, there's 2 and 3. Here, there's 1 and 3. And then at this point, 1, 2, and 3 are all stable. So this is sort of the symmetric point of the phase diagram. So what is Pirogov-Sinai theory? Well, what it says is that if beta is very large, this picture is still true. Well, I shouldn't say picture. I should say phase diagram. It's still correct up to small perturbations of the curves. Okay. So at 0 temperature, this problem is easy, or not so difficult, to determine what the stable ground states are. And what this theory tells you is that if beta is very large, the picture remains true in the sense that you can determine all of the extremal periodic Gibbs measures. So these limiting objects of this collection are called Gibbs measures. This is not maybe the best, the canonical language that we usually use to describe all the Gibbs measures, but it's an appropriate one. So you ask, what are the extremal Gibbs measures? And you get this picture. So if you've chosen the parameters h so that you're in this region, there'll only be 1 extremal Gibbs measure. While if you choose the parameters that you lie on this curve, there'll be 2 extremal Gibbs measures. So this theory is really a set of tools. It's a method. It's not a theorem that you just plug in and get this conclusion. In any given case, you have to do a bit of work. And it's actually a very powerful method. It tells you much stronger information. So another thing that you can learn that might be of interest to people in this workshop, so you can learn that the zeros so as a function of the HIs, or the HRs, lie on the coexistence curves. So when we were talking about the Li-Yang theorem at various points in this workshop, we were thinking about the zeros as functions of the external field. That's what these H's are, as the external field parameters. And Pirogov-Sinai theory is powerful enough to tell you that when you're in this low temperature regime, you actually know where the complex zeros of the partition function are. You have to choose the parameters that you lie extremely close to these phase coexistence curves in finite volume. And as the box gets bigger and bigger, the zeros, you'll only see zeros of the partition function along these lines.
You're talking about the complex zero?
The complex zeros. Yeah.
There are no complex zeros
Except in the coexistence regime, yeah. So Pirogov-Sinai theory goes back to the 70s, and this is much more recent. This is maybe like mid-2000s or so. But it's all part of the same philosophical approach to studying the phase diagram by Pirogov-Sinai theory. Okay, so now is a good time, if there's any questions about what a phase diagram means or what Pirogov-Sinai theory does, that you ask me, because I want to spend the rest of the time sort of explaining how you use this idea to study high-density hardcore model on ZD. So we only use a small fraction of Pirogov-Sinai theory. But because of connections like these complex zeros, conceivably you can answer much more detailed questions, and there are many interesting applications I would expect of Pirogov-Sinai theory to questions of interest in computer science and algorithms. So the part that we use is how to convert questions into polymer model questions. So we'll spend 25 minutes saying how do you actually do counting and how do you do sampling once you have a polymer model where you can prove the cluster expansion converges. So what I'm going to show you is how to set up a polymer model where it's possible to prove convergence, and then the rest of the story is more or less the same as Will described. So step 0 is that we want the polymers to represent deviations from the thing we expect to see, so we should rewrite the partition function in a way that makes that possible. So the first thing to do, let me just focus on choosing the even boundary condition for the sake of choosing one. So I take out the contribution from the maximal independent sets. Maybe they have size m. And then what remains, I have to put in 1 over lambda. And just so that I don't have to keep rewriting 1 over lambda all the time, I'm going to make little z lambda inverse. And z lambda of z is ze. So once I do this, what do we have? The lowest order coefficient of this polynomial is the number of maximal independent sets. Sorry, the number of maximum independent sets, the ones with the highest cardinality. And the coefficients of z are the smallest perturbations. Which is sort of getting us in the direction of having some kind of systematic polymer model representation. But the challenge of the method is basically to formalize the idea that the low order terms in z are actually representing small perturbations and proving that they're small. That's what convergence of the cluster expansion means. So let's see how to do that. So step 1 is that you fix some independent set I, and you just pick some vertex v in your graph. You call v correct if you see one of the two local pictures that I'm about to draw. So if it's correct, it should look like a ground state. The ground states are all even or all odd for the independent set model. So either I should see that v is occupied, its nearest neighbors are unoccupied, and its next nearest neighbors are occupied. Or if v is unoccupied, all of its nearest neighbors should be occupied. And none of its next nearest neighbors should be occupied. Okay, so if you see one of these two pictures, v is correct for the independent set I, and otherwise it's incorrect. Okay. So using this idea of having correct and incorrect vertices, we can start to draw pictures that are easier to draw than to write the explicit expressions for the partition function that get us close to a polymer model. So we have connected components of incorrect vertices. So let's draw a picture. For simplicity, let's choose a nice subset of ZD, like a box. And we have even boundary conditions all the way around. And I have some connecting components of incorrect things, so schematically, maybe it's something like this. So all of the shaded region is indicating incorrect. Of course, inside of some incorrect region, I could see some correct regions again. So I might have holes. And inside of those correct regions, I might have incorrect regions again. So there might be some more things here. And it can continue on and on forever. Well, not forever, because it's a finite graph, but a long time. This happens if you look at maps too. You can check on Wikipedia for the most islands within a lake. Or sorry, yeah, islands within a lake, within an island, within a lake. And I think in Canada somewhere there's like a depth 7 chain, which is surprising. Okay, so this is looking kind of like a polymer model. I'd like the things that are going to be polymers to be subsets gamma. And I want to label them with the configuration on the subset. So these are the connected components. This is the configuration. There's just a little problem here. If this is even and this is correct, then I know the boundary of this is also even, and the boundary of this is even, and the boundary of this is even. This is correct, so it must be even or odd. Maybe this one is odd, and maybe this one is even. If this is even, that means the exterior of this incorrect chunk and this incorrect chunk are both even. So these have matching external labels. That seems innocuous, but it's really bad for the polymer model representation, because the condition of being a polymer model was that things are just geometrically disjoint. And this is a long-range interaction. It doesn't matter how far apart these two components are, they still interact with one another by the condition that they have the same exterior label. So this thing is not a polymer model, so we have to do a little more work. So that's step 2. So what we do is that we group the collection of independent sets on lambda into equivalence classes. And the equivalence classes are determined by some of the objects in this picture. So they're determined by the external so the external collections of gamma and I. So what does it mean to be an external object? It means that if I start inside my connected component, I can go to the boundary without passing through any other component. So this is a well-defined notion. So I pick an independent set, I get some collection of external contours, and then I sum over all of the independent sets that would give me the same set of external contours. And if you do that, what you get is that the partition function can be written as a sum over collections of mutually disjoint and external with label E. And then you have to take the weight of all of these things. So you take the product over all of your contours, Z to some surface energy, and then inside you now have some new terms, which I'm going to need to draw a picture to explain. So when you do this resummation, you sort of recreate partition functions. And that's the weight that I need to write next. So I'm going to come back to this formula in 1 second. Let me just draw the picture first. Again, we have even boundary conditions. Let's think about this picture. So I fix all the external contours and I sum over all the possible ways that I can get them. What I see then is, again, my same two elements here. I see this. And I see this. So the difference between these pictures is that since I've summed over all possible configurations, there's many possibilities in here now. This is not determined. So this was an even boundary condition. So inside, I actually see Z, a partition function with even boundary conditions in this region. And here I see a partition function with odd boundary conditions. So these contour objects contain the partition functions in their weight. So they actually have a factor, ZE, so the graph on which this partition function lives is the interior of this contour with label E. So this could have many components. But I can still just write the partition function as the product of the partition functions because they're in disjoint sets. And I also have to take the contribution from all of the odd terms. Okay. So, good news. This is a polymer model. So the notion of disjointness is just that you fill in all the holes and you check if the two things overlap, and that's the only thing you have to check because everything has the same exterior label. But before we celebrate too much, the bad news is that how big are these weights? These weights are enormous, right? They contain partition functions in them that are like comparable to the volume of the set. So the weights are exponentially large in the volume. So if you wanted to satisfy something like the Katetsky price condition that Will was using to verify the convergence of the cluster expansion, there's no way it's going to work in this representation. And this is the point where you really start to feel the effect of having your favorite graph be ZD instead of the random regular graph. If you have expansion, it doesn't matter if it's exponentially larger than the volume. The cost from the boundary term is still going to let you win. On ZD, that's just completely false. So I didn't say explicitly what this factor is. This just measures how many particles are missing in the contour. So I'm trying to look at a densest possible independent set. So in any contour, I'm making mistakes because it's an incorrect region. So this just counts the number of particles that are being missed. Okay. So we have a polymer model. We can't prove the cluster expansion converges. So what do you do if you're someone who likes expansion methods and you get stuck? You expand again. And this is somehow perhaps the most important idea in doing, well, one of the most important ideas in Pirogov-Sinai theory, which is sometimes called the dilution trick. And like any good trick, it looks very stupid. So I can rewrite the odd boundary partition function in some region lambda. So now lambda is going to be like the interior of some contour. Well, it's that times that, multiplying by 1. This turns out to be very good. Why is this good? This term I can expand again. It's again a partition function with an even boundary condition, so I just repeat. And this term I absorb into the weight of my contours, my polymers. So if you expand ZE terms, and you do this repeatedly, what you get is the following formula. Well, it's going to be a sum over collections of polymers, gamma, that are mutually disjoint with exterior label E, because I expanded this term again. Then I get a product over all of the polymers, a weight of the polymer. And what is that weight? Well, it's like the one I had before, except now I have to include this ratio of partition functions. So it's Z, the number of missing particles in the contour itself. And in a ratio of partition functions, I have to look at the interior regions with label odd and take this ratio. So I look at that region that has odd boundary condition, I switch its boundary condition to E, and that's the term I divide by. Okay, so this is an identity. Now I have another representation for my partition function. This is another polymer model. This one is much better. So why is this one much better? Well, I no longer have these volume factors corresponding to the interior, so I could hope that my weights are going to be small. So for this polymer model, you can prove Katetsky price is satisfied if lambda is very large, or in our current notation, if Z is very small. This is not a trivial thing to do, though. The weights that we saw in earlier talks today were mostly relatively simple combinatorial things, and now I have rather unpleasant rational functions in my weights. So I don't really have time to go into how you prove this convergence, but the idea is that you induct on volume. And maybe to give you some idea of why this should be a good idea, consider a really small polymer. Like maybe it just has 2 vertices in it. There's no way there can be an interior. So this ratio is 1. So then you have good control by making Z small enough. Once you do that, you look at contours of size 1 bigger. Any of their interior components can only contain smaller contours. And you already understand smaller contours by induction. So you can control this ratio by using the cluster expansion, which you know applies because they only contain small contours.
Do you use that Z to the D actually doesn't expand, so contrary to what you used before?
Yeah, so you need some isoperimetry properties.
Working the other way, right? So
Working the other way. So it's some of that confusion might be resolved by saying that the notion of ground state that I defined is not even so good when you don't have any isoperimetry on expanders. Okay, so that's how you prove that you have the Katetsky price condition, so you have a convergent cluster expansion. So you can pretty much just use the algorithms that Will described this morning to prove the theorem. Just the one thing that you need to remark is that these weight functions are no longer so obvious that you can compute them efficiently. So that was part of Will's algorithm, was that you know that you can compute weights efficiently. So to compute weights efficiently, Well, you draw inspiration from this. You sort of do it inductively. I can compute the weights of small contours because this ratio is 1. Then when I want to compute the weights later, I can get very good approximations to both of these partition functions. So I can get very good approximations to these weights, and that's enough to make the algorithm work that Will described. It's not exactly the way he said it, but it does work. Small. To sufficient. Okay. So that's how the proof of the theorem that I've erased goes. At least in the case of subsets of ZD, you have to do something a little different on the torus, but it's an idea that you've now seen 3 times this morning. The idea on the torus is, the idea in the previous talks was that if you want to look at the Potts model partition function on a random regular graph, you break it into the mostly red piece, the mostly green piece, the mostly blue piece, and so on. And on the torus here, you just want to break it into the mostly even piece and the mostly odd piece. And the way you can do it is sort of say, look at any configuration with an enormous contour. And you can just prove by brute force that this is unlikely. If there's no really big contours, then you can sort of embed your problem in ZD again, and this notion of an exterior contour makes sense, and you can develop all of the same machinery. And if you want to sample, it's again doing it contour by contour. So I should say that in this step, there are relatively general theorems that will do this step for you. And for example, the one we used is due to Borg's and Imbri. But in general, you may have to go into the guts of this for the particular problem you're interested in. So I think that's the end of my time. So I'll stop here. Thanks.
So to begin by pointing out that in any dimension there's a critical value of lambda.
Yeah.
You're working on the large lambda side.
Yeah.
So one question is, as the dimension gets large, I guess one probably knows how the critical value behaves in large.
That's still open, actually. But it's believed to be, I think, 1 over d or log d over d, but it's actually open.
So I guess my question was sort of how the region in which this expansion converges, does that get farther away from the critical value in high dimensions or closer? Or?
It gets farther and really much further. This is like exponential d. And the truth is decaying in d. So in that sense, it's really unsatisfactory. It's sort of a problem with the hardcore model in general, is that we have no tools to sort of show any kind of monotonicity. So the reason we don't know the behavior of the critical point is sort of because we don't even know that there's actually only 2 regions. There could be other phases in between. We don't even know how to prove that that doesn't happen.
Another question over there? Any others? Okay, well, that's the end of the morning session, and I believe we come back at 2:15. So let's thank Tyler and all of this one.